So the challenge is that when you look at these low mass stars, you have a way smaller star to begin with. So that means that the amount of leftover material around it would have also been much less. And therefore, it's kind of surprising there was even enough material in the first place to make a core big enough, fast enough, that could possibly turn into a gas giant.
Giant planet around tiny star should not exist. So this planet called GJ3512b, and it's not as different in mass from its parent star as, say, Jupiter is from our star. And this caused a lot of consternation amongst the astronomers. Why is that? Are we just looking at our system and having a bias towards our particular solar system, or is this something we didn't expect to see from modeling or from what we've seen so far?
I mean, from all angles, I would say. From the theory side, it's surprising. From our own solar system, it's surprising. And from the rest of the exoplanets that we know about, which is now like 5,000, it is also surprising. So however you look at it, it is a surprising discovery. But that's kind of what makes it fun. I mean, scientists like the oddballs, and this is definitely an example of that. So the problem is the way we normally expect planets to form, at least has worked well for the solar system and many exoplanets found so far, is what we call core accretion. It's pretty simple. Actually, I can pretty much explain it, even though we do entire classes about this here. In a nutshell, the way it's thought that planets form is by pebbles essentially coalescing together. So once the star is born, you have dust and gas remaining. That's just the leftover stuff that didn't actually coalesce into the star, and it forms into a disk just due to like centrifugal forces. Basically, it gets pushed into a disk, and then that dust starts to coalesce, stick together. It's just kind of like sticky, like glue almost. It sticks together and forms larger clumps, eventually makes pebbles. Those pebbles, when they get big enough, can start to self-gravitate and then form planetesimals and planetary embryos, like the cores of planets. And then you might be done then, and that might be the end of it, and you have an Earth. Or if the core is big enough, let's say it's above about 10 Earth masses, then actually it has enough self-gravity that it will just pull in all of the gas around it to create like a gas giant, a gas envelope around it. So that's pretty much the picture that you have.
But we have to start with a core of ice or rock or this kind of thing to get. That thing has to grow quite quickly. That's kind of a key point, because stars, as they are being born, are quite violent, and it doesn't take them too long for them to basically blow off all of the gas around them. Just through the radiation they're producing. So if the planet is going to become a gas giant, it has to do it quite quick. It has to get enough pebbles together fast, and then there's some gas for it to pull in and give itself an envelope. So the challenge is that when you look at these low mass stars, you have a way smaller star to begin with. So that means that the amount of leftover material around it would have also been much less. And therefore, it's kind of surprising there was even enough material in the first place to make a core big enough, fast enough, that could possibly turn into a gas giant. So this is kind of where the tension's coming from. Like, how do you possibly have enough stuff to even make a planet that big around a star so tiny? So there is some other ways of potentially making planets, and we can talk about that if you want. But this model of core accretion is so far pretty much our accepted method of how 99% of stuff is forming. Interesting. So usually with these smaller stars, we'd expect small rocky planets close into the star. Is that right? So I think there's an example of this TRAPPIST-1, or that has these small rocky planets close by, because there's not a lot of material to make these planets out of. So what is the leading idea about how this large planet could have formed? You were mentioning we could go into this. What's the leading idea of how this could have happened? Could it have been?
Well, it's a little bit premature.
Could it have been caught in the gravity, come from somewhere else? Probably not, I guess, because
other stars would be so far away. I'm trying to think of.
Yeah, that's not a bad idea, but it's somewhat unlikely to get. You'd have to be born in a very dense sort of stellar nursery to have a chance of that happening. So in terms of what's the, you're asking like what's the consensus? This paper came out on Friday. Today it's Tuesday.
Okay, so
I don't think we've had time for a consensus to emerge
no consensus yet.
how this thing formed. Having said that, with this science paper that came out,
they gave a suggestion, didn't they?
Yeah, well, actually, they gave a suggestion, and there was even an article which was written as a sort of a commentary, which suggested this as well. And this goes back again to one of the older ideas for how planets might form, and it's called gravitational instability. It's pretty different, and it's really more akin to how stars form. So stars form through gravitational collapse of clouds. So it's like a runaway effect, right? Once you get an overdensity, then that overdensity starts to attract more stuff towards it, and then it gets denser and denser, and things just run away. And very quickly you can build stars this way. So this is how we think most stars form, and maybe even brown dwarfs and things like this are building this way. Maybe you can form planets that way as well. So once a star is born, you have this leftover stuff around it. Maybe there's enough stuff and it has enough instabilities within the disk that those instabilities could then collapse in a similar way. And that's the gas itself collapsing, right? This isn't you don't have like a planetary core, which is then bringing everything together. This is just the gas is denser in one region, and then that overdensity is drawing more and more gas onto itself.
Is that almost like it's behaving in the same way the star was formed itself, but there's less stuff left. Yeah. So it can't make the pressure and the density to become a star itself. So we get this leftover large.
It's a failed star. You could think of it as a failed star in that sense, yeah. And that is perhaps an easier way to make this planet, because that can happen very fast. When you simulate this formation process, it's extremely quick for it to work. In general, it doesn't seem to work for planets around sun-like stars. And that's because when you simulate the disks of sun-like stars, the shear forces kind of even out the disk too quickly, and thus you just can't build up those instabilities. So with the M dwarfs, it's a little bit unclear what happens, and it is perhaps possible that just the smaller scale of it allows for pockets of high density to emerge. And I think that's about as much as we can say. It's kind of speculative as to how this would work. There's simulations here. But this is one of the oldest ideas about how planets might form. And over time, core accretion basically won out the argument and turned out to keep winning in terms of its predictions. But now maybe we're seeing a renaissance of gravitational instability coming back and being able to explain some of these more weirdos in the distribution of planets we're seeing.
Interesting. So this is the ratio between the stellar mass and the planet mass is 10 times higher for this one. So it really is outside the range of the normal theory or the core accretion theories and the computer models. Although, is an order of magnitude really that important in astronomy?
An order of magnitude is like the minimum amount that
you care about.
Minimal useful unit.
I have to have a dig from particle physics, because ours is like 10 to the minus 7, and they're still worried that it's not quite accurate enough. Whereas you guys are just like 100, 1,000, okay.
It's fine. Yeah.
To an order of magnitude, you start to worry.
This is interesting. I mean, one of the interesting questions this reminded me of when I read this was there was a nice paper by Kevin Schlaufman a few years ago, and he was talking about brown dwarfs and planets which are sort of in between Jupiter and a brown dwarf. So a brown dwarf is something which is like 20 times heavier than Jupiter, but it's about the same size as Jupiter. And we don't know what to call that. Do you call that a planet, or do you call that a star? And at the moment, we just call them brown dwarfs, and we really don't know how to classify them. And he was actually showing that, with this gravitational instability model versus core accretion, that sort of around 4 to 5 Jupiter masses, it looks like there's some kind of transition happening, and maybe things above 5 Jupiter masses are actually the products of gravitational instability. And the things below that are the products of core accretion. And even though the physical properties of the two look very, very similar, they formed completely differently. And thus maybe the formation mechanism should be how we should be used in the naming.
whether you classify something as a planet or a star, or a failed star really, maybe that should be through how it formed rather than just what it looks like now.
So we might have been lulled into the naming because the things look the same at the end, but the way that they actually got there was
completely different.
Completely different.
Yeah.
Interesting. There was another point I was going to mention just as we go off this. So what would you say was the headline for this particular story?
Because you're so impressed with my headline writing.
I mean,
right? From the last one.
Grabbed me by the Jaffas last time, so you're up again.
Yeah, I think the headline is pretty fair so far. Like, you know, a world that came in from the cold or an unexplained planet is pretty good. But I mean, as a scientist, I would interpret it as evidence for a gravitational instability planet. That's how I would read it as a scientist. But maybe you might have something along the lines of hints or suggests evidence for a second way of making planets or something like that. That might be a good way.
It's a vintage planet, the comeback kid. That's what it is.
Yeah, that's I like that.
We'll go with that. Dave, thank you so much for going through those two stories with me. They're a lot clearer for me. I hope the audience enjoyed it. Thank you very much again. As I said during the video, Dave, do you want to plug your channel, which is a superb channel for videos about everything astronomy, everything exoplanets?
Yeah, it's pretty different to having a chat like this, but we take a deep dive into topics, and I kind of like to make these mini documentaries these days on various subjects. The last one we did was on how common are Earth-like planets, and we take a deep dive into the statistics and try to explain why this is so important. So if you're interested in questions like that, then come check out our channel. It's Cool Worlds, or youtube.com/coolworldslab. I'm sure there's a link somewhere on this.
Well, we can sort that. It appears by magic, yeah. No,
I look forward to seeing you over there.
Guys, it really is an excellent channel. Dave does great content, puts a lot of time into it, and you can tell that he really enjoys what he's doing and is very knowledgeable about it. So head over to Cool Worlds and subscribe. Dave, thank you so much again, and hopefully we'll have you back again when I'm confused about something else on the BBC website.
I'm sure.
Thanks a lot, Dave.
Okay.
Bye now.
No problem. Thanks for having me. Bye.
No worries. Bye.